I think it's rather appropriate. The only Welsh person in the programme this afternoon is actually going to talk about that bit of the stratigraphic column which will forever be Welsh, the Lower Paleozoic. Of course, I don't need to remind you that the Cambrian, the Silurian, the Ordovician are all linked to Welsh names. For those of you who are really into the Silurian, you'll remember, of course, that they were a tribe from southeast Wales, where we are now, which had the dubious record of once exterminating a complete legion. They didn't even send a donkey back. So the Silurians were a very tough South Walian tribe. So what am I attempting to do today? I want to talk about and ask, is there a link between, or feedback between diversity, evolution, and carbonate depositions in the early Paleozoic? Well, the answer is yes, of course, because organisms produce shells. That's going to affect carbonate systems. We know how important microbial processes are in triggering some forms of early diagenesis. So yes, there are links, obviously. But does carbonate diagenesis affect the organisms? Does it affect their diversity and their niche diversification? And that's what we'd like to present today. So our proposal is that very specific interactions took place during this interval, Cambro-Ordovician. Increased influence of the infauna, which of course is well documented, selective carbonate remobilization, cementation and reworking, and then, as a result of that, diversification of the encrusting epifauna. So diagenesis, we will argue, contributes to the global Ordovician biodiversification event, but that these effects were relatively short-lived on a geological scale. I would like to try and explain why that happened as well. So the takeaway points, if you're not interested after I've done these, you can relax and go to sleep. The increased depth and degree of bioturbation thickened the mixed layer and the taphonomically active zone during this critical interval, and displaced the zone of syn-depositional cementation downwards, such that reworking by wave and storms became less likely. This explains three critical features of the Lower Paleozoic, we think. The demise of flat pebble breccias, breccia conglomerates from subtidal settings, the subsequent peak in hardgrounds, so well documented from early to mid-Ordovician, and the later Ordovician decrease in hardground frequency. And of course, it was because of this increase in the availability of hard substrates that we see a very significant expansion in the encrusting biota. This is not rocket science, okay? If all we're attempting to do is to look at four well-documented facts from the Lower Paleozoic and suggest that they are actually very closely linked. Those are burrowing depth and thickness of the mixed zone increased during this interval, well documented. Flat pebble breccias, if you don't know what they are, I'll show some in a minute, which have been an obsession with some sedimentologists for some years. They disappear from mid to outer ramp and shell settings during this interval. Hardgrounds peaked, as I've already said, and encrusters become much more diverse. Are those facts linked, and how might they be linked? So the current interpretations would be that Sepkoski argued back in the early 80s that the demise of the flat pebble breccias was due to physical disruption caused by increased bioturbation intensity and bioturbation depth. It was a physical effect that these strange carbonates, very widespread carbonates in that interval, disappeared. And also that the Ordovician peak in hardgrounds has been interpreted. I'm sure Paul won't mind me taking this quote from him. He and I can argue perhaps about this later, but it's not the main point of the talk. That the Ordovician peak in hardgrounds has been interpreted as it says here, largely due to the prevailing calcite sea conditions which facilitated early aragonite dissolution and syn-sedimentary calcite cementation. Now that is a view which is expounded, has been expounded many times since, is in textbooks, for example, that it was seawater chemistry which somehow triggered the abundance of hardgrounds. There are a number of problems with that issue, and I'll come on to them later on, but one of the key ones is that if you look in other calcite sea intervals in the Paleozoic, or even the Mesozoic, but particularly in the Paleozoic, for example, Silurian, Devonian, Carboniferous, you do not see the same abundance of hardgrounds. So even though seawater chemistry remained the same, you don't see hardgrounds. So it can't be directly linked to seawater chemistry. So let's go through these facts one by one, just to remind you about some of these key issues. Burrowing depth and thickness of the mixed zone increased during the Cambro-Ordovician. We all know about that. This is well documented, but of course it's not just the degree, but it's the depth as well. These were contemporaneous changes with one another. And Drosser and Boccia, just to quote, depth of bioturbation is consistently less than 6 centimetres through the middle Ordovician. Measurements for the depth of bioturbation observed in strata of late Ordovician age are as much as 30 centimetres. So we do see increasing depth and intensity of bioturbation during this interval. We have a classic Drosser-Boccia diagram showing, based on the 5 main categories of the degree of bioturbation, and also a very recent plot by Tarano, I believe maybe in the audience, et al., published very recently, which again shows the same broad pattern of increase in the degree of bioturbation during that interval. Flat pebble breccias, something maybe not an obsession with paleontologists, but certain sedimentologists working in the lower Paleozoic have really published shed loads of papers on these over the years, mainly to do with the physical origins, rather less so about their geochemical origins. So what are they? Well, you can see from this plot here that they are indeed, they do peak at this particular time. Interestingly, as they peak and then decline, hardground seem to come in, which is rather convenient for our interpretation, as you'll see later on. So they reach a maximum, really, during the late Cambrian, early Ordovician. So what are they? If I can quote from Sepkoski, flat pebble conglomerates are intraformational limestone conglomerates, calcirudites, composed of rounded tabular intraclasts. They form extensive flat pebble conglomerates, which are present in the Cambrian and lower Ordovician. They are thin, under a couple of centimetres thick. Now, the data we're going to present, and was shown in the previous slide, focuses on subtidal mid to outer ramp shelf carbonates. It does not, please, it does not focus on the sorts of flat pebbles you get in periodal sequences. You get those back in the Precambrian, you get them today. They're quite happily forming in the Bahamas on tidal flats today, and they relate to the reworking of desiccation cracks and thin supertidal crusts. So in the plots we're showing you, they've been excluded deliberately because they have a very different origin and very different settings to the ones that I'll be describing. What do they look like? You may have wondered what the title of the talk, No Stone Unturned. Well, the point was that these particular stones get turned and concentrated, particularly by storm processes, and that's what they look like. They're actually just flat, thin pebbles. They can sometimes be encrusted, but mainly not. Can we be more precise then? If I said these things disappear during this interval, can we be more precise when they disappear? If we look at just one example, I know it's just one basin, but it seems to be fairly representative. If we look at the phloem of this particular basin in China, described by Louis and Zhang, and we close in on that interval and then close in again, I think you can see that this is one of the best documented, quantified examples of the relationship between the disappearance of flat pebbles and other features. So our flat pebbles are disappearing progressively through the phloem, and incidentally the amount of bioturbation is increasing. So that would fit in crudely with Sepkoski's basic idea, but we think that there's an underlying cause for that, and it's not to do with physical bioturbation. Hardgrounds peaked in abundance. The abundance for the Paleozoic peaked at this time. This plot here is taken from data from Taylor and also from Wilson. If you're unfamiliar what hardgrounds are, just to remind you, these are cementation zones at or just below the sea floor, which become exposed to the sea floor. They get colonized by various epibionts, as you've already seen, and borers, and they can form extensive continuous sheets, or particularly in the middle Ordovician, they're often broken up to form what some people have referred to as hiatus concretions, or just intraclasts, if you like. So these stones are also being turned. This is a very recent compilation by Christ et al. Seems particularly appropriate for this time of year, that again showing this Ordovician peak. This is using Mark Wilson's slightly newer compilation, 2011, showing again this dramatic peak in the Ordovician of hardgrounds and then their decline. There are other peaks, and I'll come on to those right at the end, and perhaps try and explain what they represent. So the first thing you tend to see progressively through the middle Ordovician is you see these fat, flat pebbles, if I'm allowed to describe them as that. And basically, these are broken up hard grounds. Transition between flat pebbles and true hard grounds. Progressively, you see more and more developed hard grounds as you go through the Ordovician. And of course, one of the things is that these become the sites of encrusters. Seems to be a great diversification of encrusters at this time, so they're actually easier to see. It's easier to see a hard ground when you can see evidence that something encrusted it. The last fact, encrusters become much more common and diverse through the Ordovician, no more dramatically shown than in this plot here, to show you the peak in abundance that occurred. And if I may just give you another quote from Taylor and Wilson, the Ordovician was a golden age for epizoans on hard substrates, at least for those which left skeletal evidence. Much of the increased abundance and diversity of Ordovician hard substrate organisms is due to the increase in hard substrate availability. More hard grounds, more encrusters, and easier to find the hard grounds when they're covered in encrusters. So, what about this idea that this is a geochemical effect? This is to do with seawater. That undersaturation in Ordovician seawater led to the dissolution of aragonitic shells, and that aragonite was reprecipitated as a cement locally to produce cemented seafloors. There are another number of problems with this. Kenyon Roberts, in an exhaustive and exhausting study of Ordovician hard grounds in 1995, found absolutely no direct evidence that seafloor dissolution is taking place of aragonitic fossils, using extensive material from the eastern North America. As I've already said, these hard grounds aren't common in other calcite sea intervals in the Paleozoic, so it doesn't seem to be linked to seawater chemistry. If indeed aragonitic shells were dissolving more readily in the Paleozoic, then we could look, for example, at Lagerstätten, and comparisons between skeletal Lagerstätten coming from both calcite seas and aragonite seas shows absolutely no difference in the degree of preservation, or lack of it, of aragonitic fossils. Now, to be fair, that particular case study is Carboniferous in age, but all the evidence we have is that Carboniferous seawater was of the same chemistry as Ordovician seawater. And we do have an alternative method, or mechanism, of course, of causing aragonite dissolution, and that is that undersaturation is taking place in the taphonomically active zone as a result of predominantly, but I know not wholly, of the oxidation of hydrogen sulfide to produce a weak sulfuric acid, and that is what is causing aragonite to dissolve in the taphonomically active zone. It's the main mechanism, but not the only one. And we know that lots of that carbonate can then diffuse down and create cementation in below the tars. So what we've got is a fairly standard model now that we can have a mixed biota, epifaunal or infaunal, aragonitic, calcitic, but due to this undersaturation in the taphonomically active zone, we see the dissolution preferentially of aragonite, which is more soluble. So we end up then with only calcitic fossils being preserved, predominantly. And at the same time, we're aware of early cementation taking place below the taphonomically active zone, below the zone of oxidation, taking place at or close to the zone of sulfate reduction, where alkalinity is higher. Well-established model, geochemically, it's been used to explain the missing mollusks effect that Lesley and I have been working on for some years. And also, of course, it's the mechanism now most widely accepted for the origin of diagenetic bedding in carbonates. So we want to link these facts and processes together, and we propose that as the depth and degree of bioturbation increased through the Cambrian and Ordovician, increasing the mixed layer thickness, thickening the taphonomically active zone, the zone of syn-depositional cementation, which we would argue is what produces flat pebbles, hiatus nodules, hard grounds, and diagenetic bedding, they're all texturally very, very similar, certainly in the Paleozoic, is that as this zone of cementation moved down, it was less likely to be reworked, to have the stones turned over, with time. So, the very simple model we're offering is that in the Cambrian early Ordovician, depth of mixing, the tars was very thin. The zone of carbonate precipitation was very near the surface. It was well within the depth to the seafloor that it was going to be reworked by storms and waves. As a result, you get a lot of extensive rework and give you flat pebble breccias, and also you get a relatively short residence time before the things are reworked, so they tend to be thin. Progressively with time, as the burrowing depth the mixed zone thickened, the tars thickened. This zone of carbonate progressively moved down within the sediment column, I mean a few centimetres or so, but enough to not be so frequently reworked. As a result, the zone of cementation tended to have a longer residence time, it tended to get thicker, so when it did get reworked, it would be these fat, thin pebbles, these hiatus nodules, or indeed you would be exhuming these cemented zones to produce hard grounds. But then towards the end of the Ordovician, when we know the burying depth is more significant, the tars moved down, the zone of cementation moved down, and to such a point where it very, very rarely got exhumed or reworked to produce diagenetic bedding. And also a manifestation of all this is that the thickness of many of these individual precipitated carbonates will increase with time. So, again, to put some pictures to it, so we're talking about the late Cambrian, early Ordovician. These things are forming very near the surface. They're going to be very, very thin diagenetic carbonate layers, and they're going to be reworked readily into flat pebbles. By the mid-Ordovician, they're forming at greater depth, not a lot, but greater depth. They're not as frequently reworked. They're going to be better developed. When they do get reworked, you get the picture. They're going to be somewhat thicker, or they may just simply get exhumed to produce hard grounds. And by the late Ordovician, we see this dramatic decline in the abundance of hard grounds. And our explanation for that would be that now we're at a sufficient depth for this carbonate forming sufficiently far down that it simply isn't getting exhumed very often. And in fact, if you look at most diagenetic bedding, which continues, of course, right throughout the rest of the Phanerozoic, diagenetic bedding is very, very rarely reworked. So it seems to be forming at some depth where it's not prone to being reworked, even by quite significant storms. Okay, so the argument would be that the things I've been describing, the cementation, the flat pebbles, blah, 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 all require aragonite, remobilized aragonite in which the calcium carbonate precipitates in the sulfate reduction zone. Is there enough aragonite around to be doing all this? If you look at a standard Ordovician fauna, it's going to be calcitic in character. The black here is calcite. Most of the fauna is going to be calcitic because it's going to be made of brachiopods, it's going to be made of bryozoans and so forth. Okay? But if you look at a skeletal Lagerstätten of that age, or a Lagerstätte of that age, where you have a life assemblage which has been preserved, typically by early silicification, what we find is, of course, the dominance of aragonite. So most of the living fauna was aragonite. It's, after all, this selective aragonite dissolution. That's what we see in the time average death assemblages. But here in the life assemblage, it's predominantly aragonitic. It's made of bivalves and gastropods. So there was an abundant source of aragonite to be doing this, even way back in the Ordovician, perhaps the Cambrian as well. How much aragonite, how much molluscan aragonite do you need to produce diagenetic bedding? James Wheely and co-workers published this paper a few years ago where they looked at just how much molluscan aragonite, actually how much bivalve aragonite in this case, you need to produce the typical diagenetic bedding that you get in the Ordovician. And they found that you need to produce the typical mid-Ordovician diagenetic bedding, which is about 10 centimeters thick, an average one of these diagenetic layers. You need about a production rate of about 5 grams of aragonite, molluscan aragonite, per square meter per year. And that really isn't much of a problem because these are the rates, the production rates of bivalve aragonite known from the Phanerozoic. Most of these are recent, but not all of them are recent. So you can see it's well within that range. These are actually only using adult forms. If you take into account juveniles and you take into account the input of planktic aragonitic faunas as well, then achieving 5 grams per square meter per year is really not very difficult. So we do have an abundant source of aragonite at this time. Now then, you may have noticed there were 1 or 2 other peaks on this plot here. So what about these flat pebble peaks? If you investigate these particular peaks, they all seem to relate very closely to, but not all, to extinction events and to well-documented examples of post-extinction phases of seafloor dysoxia or anoxia. For example, the work of Pritchett and others. who have argued that the reason these flat pebbles appear is because there was a very thin tas. And of course that would fit in with a Paleozoic model as well. This particular one here is a bit of an oddity, but I've just investigated that one again. It turns out to be a very large series of debris flow slumps from Portugal, and it really has a very unique origin and isn't comparable to the settings that all of these others come from. So this is a bit of a spurious one. But this idea that somehow this relates to a very thin taphonomically active zone is supported by these particular occurrences related to seafloor anoxia and extinction events. What about the peak in these hardgrounds? Well, if you investigate these examples, they either come from very shallow water Jurassic oolite shoals in the main, or Jurassic lagoons, or they are pelagic. They're, for example, related to the ammonitical Rosso facies. So these are not comparable to the sorts of examples I've shown you, which tend to be mid to outer ramp or shelf. These are either very, very shallow water grainstone bodies, oolite shoals, or they're very deep pelagic deposits. And the same applies to the Cretaceous. Most of these examples are coming from the chalk, which is not directly comparable to the environments we've been talking about, or it's coming from very shallow water shoal facies in the Tethyan examples, particularly from the Middle East. So they're not really comparable to what was going on, to the sorts of settings that these were being generated in. Just to prove we've done our homework, if you just take one particular example, you take some of the very well-documented Jurassic hardgrounds from southern Britain, from the Middle Jurassic. This is from, again, Kenyon Roberts' work. And what Kenyon Roberts pointed out was that if you look at Middle Jurassic hardgrounds, they're of very diverse origin. There are multiple chemical models to explain them, although they may all be occurring in roughly the same shallow water environments, but they have multiple origins. But he went on to show that if you look at the typical Ordovician hardgrounds of the eastern North America, they have basically the same origin. They are related to, closely related to formation in the sulfate reduction zone. So we can explain those other spikes. So in summary, increased biotic diversity through the Ordovician led to increased bioturbation, thickened the tas, and lowered the zone of carbonate cementation. This then led to less frequent reworking of the cemented zone and therefore decline in flat pebble breccias, but resulted initially in more stable substrates, hence the Hardground peak, hence the spike in crusters. Initially then this increased niche availability, if you like, niche diversification, but then that declined as this zone deepened. Of course, I've avoided talking about other factors, such as storm intensity, which some people have invoked. I've just realized how quickly I've done this. Well, there'll be plenty of time for discussion then. And Lesley warned me I should put more slides in, I didn't listen. Changes in storm intensity is another consideration, and that there could have been changes in supply of aragonite, and there probably were changes in the supply of aragonite. But why that would cause things to deepen, I don't know. So, having completely ruined my timing, I usually overrun, but I've actually finished well in time. This is unbelievable, especially for a Welshman. I'd like to thank Carl Brett, Noel James, Brian Pratt for providing some of the images, and I'd like to wish you Nadolig Llawen, Merry Christmas, and a Happy New Year in Welsh. But I'm certain there'll be questions. Thank you.